Hi everyone, this is Mrs. GA, and today we're going to learn about polynomial functions and their graphs. So a polynomial function can be defined by this equation. So a few important parts to know. N is considered the degree of the function. So n is the largest exponent. It may not always be written first initially, but if you rewrite it in descending order, it will always be that first term. And so again, n is called the degree. It's the largest exponent of your function. A sub 0, we call that the constant. Notice that that's the only term without an x value. And then a sub n, which is the coefficient of the term with the largest degree, we call this the lead coefficient. So again, it's not always written first, but if you write your function in descending order, then it would be your first coefficient. So we call this the lead coefficient. All right, so now we're going to talk about the process for graphing a polynomial function. So I know this looks like a lot, but it's really just a lot of tiny steps that we have to put together to make a single graph. So the first thing we're going to do is we're going to determine the end behavior of our graph. So to do this, we need to check two different parts. First, we have to look at the lead coefficient to see if it's positive or negative. So if our lead coefficient is positive, then as x approaches positive infinity, f of x approaches positive infinity. This just means that moving to the right, our graph is going up. If our lead coefficient is negative, that means that moving to the right, our graph is going down. So we always start by saying what's happening as x approaches positive infinity. And again, all we have to look at is the sign of our lead coefficient. Then we have to check the degree of our function, which remember is that n value. So if our degree is even, then the end behavior matches. So whatever is happening on the right, I do the same on the left. However, if our n value is odd, if our degree is odd, then the end behavior is opposite. So if I'm going up to the right, I go down to the left and vice versa. So just by checking the lead coefficient and the degree, I can determine the end behavior of our graph. So once I know the end behavior, the next thing I'm going to do is I'm going to find the y-intercept and any x-intercepts that I might have. So the y-intercept is either just the constant if you see it, or you can find it by setting x equal to 0. And then for the x-intercepts, you may need to factor first in order to find them. So once you know the x-intercepts and you know the end behavior, you need to start piecing it all together. But sometimes you're going to have what's called a repeating root. So if you have maybe a double root or a triple root or a quadruple root at a given value, you're going to have different features in your graph. So even anytime you have even repetition with a root, like if you have a double root or a quadruple root, your graph is going to hit the x-axis and actually turn around. So it's going to look kind of like a quadratic function. So it hits your axis and it turns around. So it doesn't actually cross over. So look for even repetition for that. Now, if you have odd repetition, your graph will kind of flatten out as it approaches that root, but it continues through. So the best example for that would be like a cubic graph. It kind of looks like this. So it slows down, and this is where your root would be, but then it continues through. So you do need to show that function. And then again, for the even repetition, it hits your axis and then it turns around. So you do need to watch out for these so you can incorporate them into your sketch. From there, it's just putting all of this together. So can you make a graph that has the correct end behavior, crosses at the right points, and accommodates for repeating roots? Okay, so we're going to go through that entire process together. So again, the first thing we're going to look for when we have our function is we're going to try to determine the end behavior. So you can see here that our lead coefficient is just 1. So our lead coefficient, if you multiply this out, is 1. So since it is positive, we can make the statement that as x approaches positive infinity, f of x approaches positive infinity, which is just saying going to the right, our graph is going up. So then the next thing we're going to check is the degree. So since this is already factored, I'm going to treat each factor as 1 degree of x. So I have x here, and x here. If I multiplied this out, my largest exponent would be 3. So that means that my degree here is 3. Now, since my degree is odd, I know that my end behavior is going to be opposite. So that means as x approaches negative infinity, which means moving to the left, my graph is going to go down. So these are opposites because my degree is odd. Okay, next, I need to find my intercepts. So let's start by finding the y-intercept. And remember, we can do that by setting x equal to 0. So if I have 0 times anything, I know that my y-intercept is going to be at the origin. And then last, I need to find my x-intercept or intercepts. Here I have 3 factors, so I know that I'm going to have 3 x-intercepts. So at the origin, again, I have one at -2, 0, and 3, 0. So now I have all of the information we need to be able to sketch a graph. So I'm going to just create a quick little XY axis. And again, this is just a pretty rough sketch. So first thing I'm going to do, I'm going to mark where my graph crosses my axes. So it should only cross at 0, 0, -2, 0, and 3, 0. So those are my intercepts. So my lead coefficient, again, told me that as x approaches positive infinity, f of x approaches positive infinity. So moving to the right, my graph goes up. And then since my degree was odd, I have opposite end behavior. So moving to the left, my graph goes down. So I need to find a way to connect these lines and only cross at these 3 points, which would look something like this. Now again, this is just a really rough sketch. You could have more accuracy here and here if you just made a t-chart. But again, this gives you a really good idea of what that function looks like. Okay, let's try another one together. So we're going to go through the same process. Let's start by looking at the lead coefficient. I see that in this case, our lead coefficient is -1. So since that's negative, that means that as x approaches positive infinity, f of x is going to approach negative infinity. So moving to the right, my graph is going to go down. Now I need to count the degree of this function. So I'm going to count how many zeros I have. I have 2 here, and then another one, and then another one. So 1, 2, 3, 4. My degree is 4. So since my degree is even, I know that this end behavior is going to match. So that means that going to the left, my graph is also going to go down. So again, even degrees have matching end behavior. Now I need to find the intercepts. So let's start with the y-intercept. So if I set x equal to 0, we get y equals negative, and then here we have -4 squared times 3 times -6. So you can see I just replaced all of my x's with 0. So if you multiply this out, we actually get y equals 288. So our y-intercept is at 0, 288. So again, we're just going to do a really rough sketch of this. It won't be drawn to scale, so don't worry about a really large y-intercept. Okay, now we need to find the x-intercepts. So I can see that I have an x-intercept at 4, 0. And this one I'm going to make a special note that this is we call it a double root because of the squared. So it's like I have this twice. And remember, that creates a special feature when we graph. And then I have one at -3, 0 and one at 6, 0. So now I have all the information I need to sketch a graph. So here, let's say this is +4, let's say this is 6, and again, this is not drawn to scale, and then let's call this 288. So I know that my graph can only touch at these points. Now let's look at the end behavior. Again, moving to the right, my graph is going to go down because it's negative lead coefficient. And then moving to the left, my graph is also going to go down. Remember, since the degree is even, my end behavior matches. So now I need to find a way to cross only at these points and attach these two arrows. However, we need to be careful with this double root. So remember, at the double root, so at 4, I'm not going to cross over. I'm actually going to touch and turn around. So let's see if this makes sense. So this one, it will go right through -3. It will go through my y-intercept. It will turn around eventually. It touches -4, turns around, and then goes back through 6. So again, if we didn't have this feature here, we wouldn't be able to piece it together to have the correct end behavior. So again, any single root, it just goes straight through, like at -3 and 6. But at a double root, your graph is going to turn around at your x-intercept. Okay, let's try another one together. So this one, we can see that the lead coefficient is 3, which tells us, since it's positive, that as x approaches positive infinity, f of x is going to approach positive infinity. This means moving to the right, our graph goes up because it's positive. Now let's see if we can find the degree. So I have 1, and then I have 3 here, and then 1 here. So 1 plus 3 plus 1 is 5. So my degree is 5. So since it's odd, I have opposite end behavior. So as x approaches negative infinity, f of x is going to approach negative infinity. These are opposites because my degree is odd. Let's find the y-intercept. So if I set x equal to 0, I get y equals 0. So it's 0, 0, because again, I'm multiplying everything by this 0, so I don't even have to check. For my x-intercepts, I have 0, a triple root at -2, and 5. So I have 0, 0, -2, 0, which is a triple root. And then I have 5, 0. So again, now I have everything I need to sketch a graph. So I'm going to make my xy axis. Okay, so let's say I'll just do this, 1, 2, 3, 4, 5. Okay, so I can only cross at 0, -2, and 5. For my end behavior, to the right, I'm going up. To the left, I'm going down. And then remember, we have a triple root at -2, which means my graph kind of slows down, it flattens out, but it does keep going. So my graph will look something like this. So again, it goes like this. It makes kind of this flattened out S shape. And then it's going to cross over here. And then it's going to cross back over to head towards positive infinity. So notice, right, my graph needs to turn around here. I cannot cross my y-axis at any other place than the origin. So again, this is what a odd repeating root looks like. It kind of slows down, but it does cross over, and then I cross over once, and then I cross over once for single roots. Okay, so this one you'll notice we are going to have to do a little bit more work because it's not factored for us, but we can start the problem in the same way. I can see that our lead coefficient is -1. Remember, it's the coefficient of the term with our largest exponent, so it's -1. That tells us that as we move to the right, our graph is going down. So as x approaches positive infinity, f of x approaches negative infinity. Our degree, in this case, is 3. Remember, it's our largest exponent. So that tells me that our end behavior is opposite. So as I move to the left, my graph is going to go up. So moving to the right, I go down. Moving to the left, I go up. And again, that's because our degree is odd. For the y-intercept, I can see that my constant is 0. So my y-intercept is again at the origin. Now to find the x-intercepts, we are going to need to factor it. So let's say 0 equals, and we'll set it equal to 0 so we can solve. So first thing you hopefully notice, there's a GCF. We can factor out negative x, leaving us with x squared plus 6x plus 9. And then we have negative x and then x plus 3 squared. So I can see that we have an x-intercept again at the origin, and then at -3, 0, but this one is a double root. So we know that's going to touch our axis and turn around. Okay, so now we have everything we need to sketch a graph. Okay, so here's -3. So we can only cross our axes here and here. Again, for end behavior, moving to the right, I'm going down, and moving to the left, I'm going up. We have opposite end behavior. And then let's talk about this double root. So I do need to touch -3 and turn around. So my graph will do this. It will touch -3 and it will turn around. But then I need to cross back over at the origin and then head towards -infinity. Okay, let's try another one together. So here, again, we will need to factor to find our intercepts, but let's start with the lead coefficient, which in this case is 1. So since our lead coefficient is positive, we know that as x approaches positive infinity, f of x approaches positive infinity. Moving to the right, I'm going up. Our degree, again, our largest exponent, is 3. Odd degrees have opposite end behavior. So that means that moving to the left, our graph is going to go down. Notice these are opposites because the degree is odd. For the y-intercept, I can see that my constant is -4, so it's at 0, -4. And then for the x-intercepts, I'm going to need to factor. So I'm going to try factor by grouping. So if you group these first two terms, I have a GCF of x squared, leaving me with x plus 4. If I group these second two terms, I can factor out -1, leaving me with x plus 4. And since I see a common shared factor of x plus 4, I can group my coefficients. So I have x squared minus 1 times x plus 4. And then hopefully you see that we can factor this a little bit more using difference of two squares. So here I can see that my x-intercepts will be at -1, 0, 1, 0, and -4, 0. So here we have everything we need to sketch a graph. 1, 2, 3, 4. Okay, and I can only cross at my intercepts at 0, -4, -1, 0, 1, 0, and -4, 0. So these are the only places my graph can cross either of my axes. So again, for my end behavior, I know that moving to the right, I'm going up. Moving to the left, I'm going down. It's opposite because the degree is odd. And everything is a single root. So it's just going to cross right through. It won't turn around. It won't slow down. It goes straight through. So I'm going to go up and then down and then cross and then up like this. Now again, I don't exactly know at this point how high this graph goes here or exactly where it turns around in between. The only way to get a more accurate graph would be to plug in some extra points, because maybe our graph actually looks something like this. It could actually go way down before it comes back up. So we don't know unless we, again, plug in some extra points, but just based on this information, we can still get a very, very accurate graph and have a really good idea of what our function looks like and where it's positive and negative, so on and so forth. So again, it is a rough sketch, but it is still relatively accurate. Okay, that is all for today's video. Thank you so much for watching.